As we said, there are two common protocols in the network layer. One is the IP version 4 and the other one is IP version 6. IP version 4 encapsulates the incoming segments from the transport layer into an IP packet, and it adds an IP header which actually looks like this. The length of the IP header is 20 bytes at minimum, and it can extend all the way to 60 bytes. So the minimum length for the IP header is 20 bytes and the maximum length is 60 bytes, in which case it adds some option fields, which is optional. The 20 bytes are divided, as we can see here, into different rows. Each row here is 32 bits or 4 bytes, as we can see. So the first length is the version, and it's only 4 bits, and this actually identifies the version of the IP address, whether it's version 4 or version 6. Another field which has a length of 8 bits or 1 byte, which is what we call differentiated services, or what we used to call before the type of service. And this field is used for quality of service. So this is this field is divided into 2 parts. The first 5 bits are representing the differentiated services code point, and this is like a priority of the packet. As we have explained before, each packet will have a priority to identify whether this is a video traffic or audio traffic or data traffic, and based on that the router will route the different packets according to a certain priority. The last 3 bits, they actually mark what we call explicit contention or congestion notification. Again, explicit congestion notification. And sometimes the router uses that to inform the sending node that there is a congestion on the route, which means that if we imagine that this router is an intersection and there are so many cars arriving on the intersection that the intersection cannot handle, there is a traffic jam, in which case the router sometimes uses that field to indicate that there is congestion on the router boards. The next field is 1 byte, and it represents what we call time to live. And the time to live represents actually the time that the packet can live inside the network. As we said, there are some rare scenarios where the packet can get routed in a wrong way inside the network, and in this case it gets circulated inside the network forever. So in order to prevent the packet from circulating in the network forever, we use that time to live to indicate the time that the packet can live inside the network. This time to live field is 8 bits, which means that the maximum time for a packet is 255, and what happens is that at each router this time gets subtracted by 1 or gets decremented, in which case the maximum number of routers that this packet can follow through is 255 routers. The protocol field, or by the 8 bits for the protocol field, they indicate the protocol in the higher layer, whether we're using TCP or UDP. As we have mentioned in the Ethernet or in the data link layer, there is always a field that indicates the protocol in the higher layer. And of course, those 2 rows, each one is 32 bits to indicate the source IP address and the destination IP address that we will talk about later. The second part of this header, it concerns with how to identify and validate the IP packet. So there is the 4-byte field of the internet header length, which represents the length of the header. As we can notice is that the header length can get from 20 bytes to 60 bytes. So how can we represent the length 20 or 60 in a 4-bit field? Well, the header length is used to represent the number of 32-bit words of the header, which means that the number of rows inside that header, which means that 20 can be represented using number 5, which means that 5 times 4 bytes, which is 32 bits, will constitute the 20 bytes. And 60, of course, is the maximum length, which can be represented by 15, which is 4 ones using the internet header length. As we know, if we have 4 bits, the maximum number that we can represent using 4 bits is 15, which means 15 times 4 is 60 bytes, which is the total length of the header. There is also the total length field, which is 2 bytes, and this indicates the total length of the entire IP packet, including the header and the data. And the data, of course, can have variable size, and the maximum size for the IP packet and the data can be up to 2 to the power 16, which is the length of this field here, which is around 65,000 bytes. There is that identification field, which is used in case of fragmentation. So as we said, sometimes the router or the node might have to fragment the IP packet into several fragments, in which case the identification number will identify the fragment number inside the total IP packet. So the identification field here will be incremented for different fragment to indicate that this is fragment 0, 1, 2, 3, and so on. And those two fields, the flags and the fragment offset, will be used to recover this fragment to form the entire IP packet, or to recover the IP packet back again. The flag field here will indicate that there are some incoming fragments that are part of the same IP packet, and the fragment offset indicates the pointer of this fragment in the entire IP packet. So using those 3 fields, we can concatenate the fragments back and form the original IP packet. And finally, the header checksum, which is used to check the integrity or the correctness of the IP packet, and if there is any error that happens within the IP packet, the whole packet will be dropped by the router. The last part in this section summarizes the IP version 6 protocol, and the motivation for IP version 6 is as follows. Well, the expansion of the great growth of the number of hosts on the internet has created a huge challenge for IP version 4 to accommodate or to provide enough IP addresses for all the hosts on the internet. In other words, because of the uniqueness requirement of IP version 4, there is no enough IP addresses that cover all the hosts on the internet. Also, due to that great growth, there is a huge expansion in the routing table on the routers, and that really slows the processing of the IP packets and consumes huge amount of memory and processor resources on the internet routers. There's also that problem of lack of end-to-end connectivity because of the shortage of the IP address. There are some techniques like network address translation, which allows the different hosts to share the same public IP address on the internet. So, for example, in our houses, we have many of the hosts that share the same public IP address that we receive from, for example, Ooredoo or any other service provider. That really creates some kind of hidden nodes from the internet. In other words, our local hosts inside our houses will become really hidden from any external node on the internet. So there is a complete isolation for the end-to-end connectivity for the hosts that use network address translation. So instead, IP version 6 tried to resolve this issue by first increasing the address space. Well, the IP address version 6 has increased from 32 bits all the way to 128 bits. That actually increases the domain for the IP address from, like, for example, 4 billion in the case of IP version 4 to 340 undecillion IP addresses using IP address version 6 on the internet. That creates tremendous address space that can be used by some trends like Internet of Things and things like that. Another improvement that came with IP address version 6 was the improved packet handling. IP version 6 header tends to be significantly simplified, or it has fewer fields. So even though the IP version 6 header is larger by using larger domain addresses, but then the header tends to be more simplified compared to IP version 4. This actually improves the packet handling and improves the efficiency of processing these fields on the routers. Another improvement was the elimination completely of the network address translation. So there is no need for network address translation. There is no need for multiple sources or multiple nodes to use or to share an IP address, since we have enough address space that covers all the nodes on the internet. Also, another feature that came with IP address version 6 was its integrated security. So IP address version 6 natively supports security and privacy capabilities. So as we can see, this is the header for IP address version 4, and when we switch to IP address version 6, we will notice that the header has been significantly simplified. As we can see, the header is a lot cleaner in the case of IP address version 6, which improves the efficiency of packet handling. So some fields like these yellow fields have been kept for IP address version 6. Some fields have totally disappeared, like these purple ones, and some nodes they have they have some replacement in IP address version 6, as we will see in a minute. This simplified header structure for our IP address version 6 has some advantages. As we have said, routing efficiency and routing performance has been improved because of the simplified header. There is no requirement on processing of a checksum. As you can see here, there is no checksum field at all in IP address version 6, so we don't have to check the correctness of the packet as it flows through the routers, which also speeds up the processing of the packet. There's also a simplified and efficient extension of the header. So as we will see, this next header points to another extension of header in an unlimited way. So we can use this next header to point to the protocol on the higher layer, or point to any other protocol that is used after this header. Also the introduction of this flow label field has allowed us to represent all the end-to-end flows from the source to the destination, and this really allows the router to provide really fine-grained quality of service per flow. So even if we have multiple video flows end-to-end, we can discriminate between all the video flows and give each one a specific identifier, which allows the router to to treat each flow differently. So that creates more granularity in providing quality of service. So this is the protocol fields. Just like IP address version 4, we have the version, and here the version field will refer to IP address version 6. The traffic class corresponds to the differentiated service field in IP address version 4, and it's also divided into differentiated services code point for using 5 bits and 3 bits used for the explicit congestion notification. So that corresponds to the differentiated services field in IP address version 4. The flow label, as we said, is 20 bits, and it's used to identify the end-to-end flow to provide fine-grained quality of service per flow for the end-to-end traffic. There is the payload length, which again corresponds to the length field in the IP address version 4, and it refers to the length of the entire packet, including the header and the payload. The next header field is kind of interesting because not only does it indicate the protocol in the higher layer, like the case for IP address version 4, but it can also point to any option, any protocol, any other protocol that is used. So you can actually have a payload that that uses IP address version 4 header, for example, and in that case, this next header will point to the next header, which is using IP version 4. So you can really encapsulate any other protocol inside IP address version 6 protocol. So you can encapsulate UDP, TCP, you can encapsulate ICMP, you can encapsulate IP address, IP packet using IP version 4 as well. So this next header always points to the next header in the IP address version 6 packet. The hop limit corresponds to the time to live field in IP address version 4, and it also refers to the number of hops, the maximum number of hops that this packet can travel. And then we have the source address and the destination address. Each of them is 4 rows of 32 bits, so that that actually includes 128 bits for the source and same for the destination.